So here's our mole road that we started in chapter 6. Remember, we started with Avogadro's number, talking about molecules and atoms, and we introduced our concept of the mole. And then the most critical part of this mole road, what makes it all possible, is being able to convert from moles of A to moles of B. So remember, this was the only way that we can convert between two different compounds, is we have to go to moles and to moles, and we use our stoichiometry, okay, or the coefficients of our balanced chemical equation. Then the most used pathway that we used in chapter 6 was going from grams of compound A to moles of A to moles of B to grams of B. Now in chapter 6, we now have two more pathways that we can take. Okay? So in order to get to moles of A, if we're dealing with a gas, we can start with the volume of A. Okay, in other words, this is going to be a volume in liters, and it has to be a gas, right? Because the ideal gas equation has it right in there, has to be a gas. We can't apply this to liquids or solids. We'll learn different ways to do that in chapter 8. So we can get from the volume in liters of gas A to moles of A, and we can do that. Let me switch colors here. We'll use green for gas, G and G. Is we're going to use our ideal gas equation, okay, our Puvnert. This pathway always works. Okay, that's always going to get us from the volume of A to moles of A, as long as A is a gas. Then, once we get to moles of A, we can convert to moles of B. And if B is a gas, then we can also figure out the volume of B in liters. Again, as long as it's a gas, using the ideal gas equation again. The other pathway that we developed was the shortcut. Okay, and again, this will always get you to where you're wanting to go. Okay, the shortcut is just if certain conditions are met, you don't have to do a full calculation using Puvnert. Okay, so kind of our shortcut for this, I'll put it over here so I can show it kind of a shorter arrow to indicate that. Okay. This is also, we can get from volume of A in liters of a gas. The important part is that this is at STP. If we are at STP, we can use the molar volume, right? Our 22.4 liters is equal to 1 mole. Okay, so that says 22.4 liters equal to 1 mole. Okay, that's our molar volume of a gas. Same thing over here. If we're still at STP once the reaction has occurred, okay, we can also use that shorthand over here to get to the volume of B in liters of our gas, as long as we are at STP. And that's 22.4 liters. I just kind of use that as a reminder of how we do that conversion. So the values shown in green here, those are basically what we've added to our mole road for chapter 7. So let's go back to our notes and show an example where we can utilize this mole road. Okay, and I'm going to choose an example that's not at STP so that you can see the full pathway of going from volume of gas A to moles of A to moles of B to volume of gas B. All right, so it's just the video. Get focusing going. Perfect. So now I'm basically looking at, we want the ideal gas law combined with stoichiometry. So at a temperature of 415 degrees Celsius and a pressure of 725 millimeters of mercury, how many grams of ammonia, NH3, can be produced when 4 liters of nitrogen dioxide react? And we are shown a balanced chemical equation. We have 4 nitrogen dioxides in the gas phase, plus 6 waters, also as a gas. And we're going to produce oxygen in the gas phase and ammonia. So we're dealing, we have a temperature here and a pressure here. So I'm going to kind of list my Puvnert values out, my ideal gas values. So I have my pressure is 725 millimeters of mercury. What units do I need that in? Remember, I need to convert that to atmospheres. I'm given a temperature of 415 degrees Celsius. And what units do I need that in? I need that in Kelvin. So I'm going to add 273. So I get what? 688 Kelvin. And what we're looking for, and basically what we need, is we're looking for grams of ammonia. And we're going to react 4.00 liters of NO2. So what units do I need my volume in? I need those in liters, so We don't have to do any conversion there. I've been given pressure, volume, and temperature. R value is always given to us, so we have 0.0821 liters times atmospheres divided by moles Kelvin. So I know that I can use my ideal gas equation to calculate N. In this case, what are my units of N? And what am I going to be solving for? So my N, remember that's going to be my moles. But moles of what? So in this case, we're dealing with a chemical reaction, so we have to be very careful what exactly these values of Puvnert here are corresponding to which compounds. Okay, so when we know that we're reacting 4 liters of nitrogen dioxide and we're using that in our Puvnert, okay, that means whatever we calculate here, that's going to be moles of NO2. So we can use our ideal gas equation to get our moles of NO2. And we are trying to get to grams of NH3. And how is the only way that we can convert from one compound to another? Hopefully you're getting tired of that question and it's becoming redundant and you're yelling at your computer. That's a good sign. Okay, if we are at moles of NO2, the only way to convert from NO2 to NH3 is we have to use stoichiometry, meaning we have to go from moles of NO2 to moles of NH3. Okay, that's the only way that we can get to any sort of values of NH3. So we are basically going to, kind of our plan here, we are going to use Puvnert to calculate our moles of NO2. Then we're going to take our moles of NO2, convert that to moles of NH3. And then we're trying to get to grams of NH3. And we can do that using our molar mass. So if we look at our mole road here, okay, zoom out here a second, is we're starting over here. We have a volume of our gas. So this is our volume of NO2. We're going to use Puvnert to calculate moles of NO2. Then use stoichiometry to go from moles of NO2 to moles of NH3. And in this case, we're asked for grams of NH3, not volume. So we're going to go from moles of NH3, use molar mass, to get to grams of NH3. So we're going from the volume of A, volume of NO2, moles of NO2, to moles of NH3, to grams of NH3. And that's the pathway that we're taking in this particular problem. If you're feeling bold enough, go ahead and try that pathway out. Try and do this calculation. Okay, pause the video, take a stab at it. You can always unpause it, get a little bit further. Maybe you get stuck on Puvnert. See if you can get Puvnert, and then pause the video again and try and complete that calculation. Okay. Does not hurt to make mistakes when you're going to have the answer given to you. So give it a try. I really encourage you guys to pause the video and give this a try on your own. All right. So one calculation we have to do before we can do our Puvnert is we need to convert our pressure. So our pressure conversion, we want to go 725 millimeters of mercury. Go from millimeters of mercury to atmospheres. So I'll grab my calculator here. We want 725 millimeters of mercury times 1 divided by 760. 3 sig figs there, so 3 sig figs here. I have 0.9539 as my calculator given answer, so I need to round my 4 up. So I get round the 3 up to a 4. So I have 0.954 atmospheres. Now I'm ready to plug that into ideal gas equation. So I have PV equals nRT. I'm looking for N, so I want to solve for that. So I'm going to divide both sides by RT. And this is going to give me N equal to PV divided by RT. I plug my values in. My pressure is 0.954 atmospheres. Times my volume, 4.00 liters. Divide by my R value, 0.0821 liters times atmospheres, divided by moles times Kelvin. And my temperature is 688 Kelvin. Looking at my units before I do my calculation to make sure I did my algebra correct over here. I have atmospheres in the numerator, atmospheres in the denominator, so those cancel. Liters in the numerator, liters in the denominator, so those cancel. Then I have Kelvin in the denominator, and then Kelvin in the denominator of the denominator, which makes that the numerator, so those cancel. And I'm left with my moles in the denominator of the denominator, so that makes that into the numerator. So I am in fact solving for moles. I'm going to plug this into my calculator. So I have 0.954 times 4 liters divided by, okay, here's a critical calculation. Okay, we have 2 values in our denominator here, so you want to make sure when you plug this into your calculator that you make sure that calculator is as smart as you are, and you have to have both of those numbers in parentheses to keep them in the denominator. So we have 0.0821 times 668 end parentheses, and we want 3 sig figs, so we have 0.0676. So my calculator gave me 0.0675579998. Okay, this 0 here is not significant because we haven't hit a non-zero digit yet. So I have my 6, my 7. This was a 5, but I had to round it up to 6. And this is going to be moles of NO2. If you put this into your calculator incorrectly, okay, if you don't use the parentheses, you're going to get a very large number. You're going to get 31,978. Okay, if you got something in the tens of thousands, okay, you did not put this in parentheses properly. Okay, so make sure that you enter in numbers to make sure your calculator is as intelligent as you all are. All right, so we have our moles of NO2. Okay, so we're here in kind of our plan. We want to go from moles of NO2 to moles of NH3 using our stoichiometry, and then moles of NH3 to grams of NH3. And so we can do that all in one railroad. So I'm going to take my moles here. So I have 0.0676 moles of NO2. I want to go from moles of NO2 to moles of NH3. We're going to use our coefficients of our balanced chemical equation. So moles of NO2, we have a 4 out in front. Moles of NH3 also have a 4 out in front. Then my last step is to go moles of NH3 to grams of NH3. We use our molar mass from our periodic table. So nitrogen is 14.01 grams per mole. Hydrogen, we have 3 of them times 1.008. So 17.034 grams per 1 mole. Remember, molar mass is always per 1 mole. It's independent. It has nothing to do with stoichiometry. It's always per 1 mole when you're doing your molar mass conversion. So we can plug this into our calculator. We have 0.0676 times 4 divided by 4, which is the same, just plugging it in to show you, times 17.034. I get 1.1514984. We're still working with 3 significant figures, so I have 1.15 grams of ammonia. And that is my final answer.